So hi everyone, welcome to Microprocessor and Interfacing course. So now we are going to discuss architecture of 8086. So this is the architecture of 8086. So we'll see this particularly BIU and EU. This is bus interface unit and execution unit. Then we will discuss one by one what is this instruction queue and ALU, flags and general purpose registers, segment registers. So this and all we will discuss one by one. So first the responsibilities of BIU and EU we will see. So BIU generates 20-bit physical address. So it can generate 20-bit physical address. There is a formula to generate the 20-bit physical address. What is that 20-bit physical address? Why we need to generate that? How the processor can generate? So that and all we will see one by one. Then it is used to fetch the instruction from the memory. Then it can transfer data to the memory as well as from the memory, as well as to the input output device, as well as from the input output device. And it maintains this 6-byte prefetch instruction. So in this instruction queue, 6-byte information the processor can prefetch, and those 6-byte informations will be waiting in this queue. So these are the responsibilities of BIU. First one is it can generate 20-bit physical address, and it can fetch the instruction from the memory, and it can transfer data to the memory as well as to the input output device. Similarly, it can take the data from the memory or from the input output device. And it is maintaining the prefetch instruction queue where the 6-byte information can wait in that queue. Next one, EU. EU means execution unit. BIU means bus interface unit. EU is responsible for execution of instruction from the BIU, and it tells BIU from where to fetch instruction and data. So EU will inform BIU from where the BIU need to fetch the instruction from the external memory. Okay, so we will see all these things one by one. First we are going to discuss external memory. So BIU, we know it can generate 20-bit physical address. It is used to generate 20-bit physical address for external memory access, and it can fetch instruction from the memory. So now we'll see, this is the external memory we have, and the size of the memory is 1 MB. This is the external memory. So as we already discussed in the last class, 1 MB, if the memory size is 1 MB, then the number of wires would be 20. And each address here, for each and every memory locations, one address will be there, and each address consists of 20 bits, right? So we'll see how BIU going to generate 20-bit physical address, but before that we need to see this external 1 MB memory. Now we'll see what is memory. Memory is connected externally. Here memory is connected externally. See here, it is connected externally. It is not within this processor. Processor is here and memory is connected externally. 8086 is capable of addressing 1 MB memory. So 1 MB memory means each address consists of 20 bits. We can access any location of memory. See this one, here we have so many registers. Okay, group of register is nothing but memory, right? So here one location, here one memory location, here one memory location, like that we have so many memory locations. So total size of 1 MB. See, for example, first memory location will be represented with address. Already we discussed each memory locations will be represented with address, right? So for that address, here totally how many bits we used? 20 bits we used. These are hexadecimal value actually. 5 hexadecimal digits we given, which means 5 into 4, 20 bits are there to represent each memory location. Okay, start from 0, 0, 0, 0, 0. And my required location is somewhere in this memory. Starting is 0, 0, 0, 0, 0 and maximum value will be FFF 5 Fs. Okay, no, FF, FF, F. This is also hexadecimal value. So starting memory location we can call it as base location, and final memory location we can call it as top location. In between this base location and top location, somewhere my required location is there. That required location's address is 20005, and remember this is hexadecimal value, and if you convert this into decimal then you will get 20 bits. So this is 20 bits address, 20 bit address, 20 bit physical address. Okay, your processor will be able to addressing 20 bit actually. It can generate 20 bit, as I told you. BAE can generate 20 bit physical address. That 20 bit physical address is this only. Okay, now what is this offset? Offset means distance of required location from the base location. Offset, what is this offset address? See, this is the base location. Base location nothing but starting location. From starting location, my required location is how far? Your required location is how far from the base location. That distance we can call it as offset address. That distance is called as offset, right? So you will come to know where this offset will be and why we need to use, from where we need to use, that and all slowly we will discuss. So remember, external memory means totally 1 MB memory size, and each memory location consists of 20 bits, and starting memory location we call it as base location, and final memory location we can call it as top location, and starting memory location represented with 0, 0, 0, 0, and final memory location will be represented with FF, FF, FH. Okay, and what is offset also? Offset is nothing but a distance of the required location from the starting location, or we can say base location, right? Now one example we have given. Suppose in this tray many plates are arranged. Okay, this is a base plate, which means starting plate, and this is the final plate. So in this tray my plate is here. Okay, so if I wanted to locate where my plate, where in which place my plate is located, in which which rack, in which rack my plate is placed. To identify that, I need to count from the base. From the base is starting value, that is 0, then 1, 2. From here if you see 1, 2, 3, 4, 5, no? Yeah. So then the distance is 5. So that we can call it as offset. So it's an analogy for your understanding purpose we given. So plates are arranged. Somewhere my plate is there. How can I track my plate from the base location? So just compare this with this, then you can understand what is offset. Okay. Now we'll see how to generate physical address by using segment address and offset address. We know already what is offset address. Segment address is nothing but base address. Already I told base address of this. Here base address is nothing but 0, 0, 0, 0, 0. Okay. Starting value is nothing but base address. Offset is nothing but distance. Okay. So now we are going to discuss how to generate physical address, 20-bit physical address by using segment address and offset address. So here we have given one analogy for better understanding. If you take a textbook, in a textbook many chapters will be there. Okay. So in one particular concept I wanted to refer. Okay. Generally what we will see, that particular concept is in which chapter. In that chapter, in which page number the particular concept is there in that textbook, right? So the chapter number is, for example, chapter number is 3. In that chapter 3, 50th page my concept is there. Okay. Chapter 3 is nothing but segment address. 50th page in that chapter 3 is nothing but offset address. I hope you understand what I am telling. Chapter 3 is nothing but segment address. In that chapter, 50th page your concept is there, like that I told, no? So that 50 is nothing but offset address. In that chapter, how many page I should cross to reach my concept, to reach the page where my concept is given, right? So offset is nothing but a distance from the base location, right? So about this CS, SS, DS and all we will discuss later. Now I hope you understand what is the difference between segment address and offset address. Segment address is like a chapter number in the textbook. Offset address is nothing but a which page number I wanted to refer in that particular chapter. Now formula to calculate physical address. So physical address equal to segment address into 10. This 10 is hexadecimal value. Remember, if you wanted to write in decimal, then you need to write 16. Okay, into 16. If it is in hexadecimal value, then you can write 10. Okay, plus offset address. So formula is physical address equal to segment address into 10 plus offset address. Physical address we can call it as memory address. Segment address, another name is base address, just now we discussed. Offset address we can call it as effective address. So this is the formula, very important formula. Now we have given one scenario. Here we have given a physical address, here we have given a segment address and offset address. Then you need to calculate the physical address of memory location. 20-bit physical address we are going to calculate. Now they have given 0A51 colon CD90H. So both are hexadecimal values. So whenever colon given, the first value you should take it as segment address. Next value you should take it as offset address. Sorry. So segment address is here 0A51. Offset address is CD90. Okay. Now we'll see how we are going to calculate physical address. Already we know the formula. Just now in the last slide we discussed. Physical address equal to segment address into 10 plus offset address. So now segment address is given, that is 0A51. So 0A51 into 10, and offset address also given CD90. Put that value CD90. Then after multiplying we will get 0A510. Then add this CD90 with this. Finally we will be getting 172A0. So see, this totally 5 values are there. 5 hexadecimal values are there. 5 hexadecimal values are there. 5 into 4, 20 bits. Right? So this is a method to calculate physical address, 20-bit physical address. Now see, again we came back to this architecture. So now here this is the external memory. What is the size of this external memory? 1 MB, right? So somewhere my data is there. My data is 00001111. Okay. This I wanted to fetch. Instruction or data, whatever. This I wanted to fetch. So first to fetch this information, what you need? You need a address, 20-bit address, to access this memory location. In this memory location, my required information is there. So first I need a physical address, 20-bit physical address, right? So see this adder circuit. In this adder circuit, whatever the formula we did just now, segment address into 10 plus offset address, that this particular calculation will be happening in this adder circuit. After doing this calculation, we will get the physical address, right? So now this calculation done, then this adder circuit having the physical address, 20-bit physical address we can say, or otherwise we can say memory address. So that is 20000, right? Now this 20000 is the address this BIU wanted to connect with the external memory, and this BIU wanted to fetch the information which is stored in this 20000 memory location, okay, in this address. Okay, now for that we need to use which one? Address bus we need to use. See, this address bus is connected. Now 20000 is this address bus going to track the memory location. Which memory location? 20000 memory location. In that address, see this address is flowing in this 20-bit address bus, right? This can carry 20-bit address, right? So now it reaches that particular memory location. Now this information the processor wanted to fetch. This instruction or data the processor wanted to fetch. So to take that data, we need to use data bus. See, this data bus is connected now. Now this particular information is traveling through this data bus, and that particular information is waiting in this queue. This is called instruction queue, prefetch queue. 6 byte at the processor BIU can keep in this instruction queue, right? So now the first information is waiting here for processing, right? So this instruction queue will work like first priority, like it will execute the first data in first priority, like that, right? So see this, first we need to know what is instruction queue. See, in this memory some datas are there, okay, and BIU going to fetch this datas. See this, your BIU fetching the data from here, from this memory location 20001, 2002, 2003, like that. Total 6 byte data your BIU going to fetch from the external memory. Just imagine this is external memory and this is your instruction queue, okay. Now first data been fetched and it is waiting here. Similarly, all the 6 datas we fetched from the external memory, and all these 6 datas are waiting. See in this, see all the 6 datas are waiting here. All these 6 datas are waiting in the instruction queue, right? So this is nothing but instruction queue, okay. Why we need to use this instruction queue? This instruction queue actually increase the speed of processing, okay, and this instruction queue will work on the basis of first in first out. Already I told FI FO basis this will work. and this instruction can store 6 byte of information in the queue, in this register, right? Now I hope you understand what is instruction queue, right? So this 6 bytes of information are waiting in this queue, whereas this is being executed, which means in the execution unit this particular data is being executing, and the next 6 bytes of information are waiting in this instruction queue, right? So now see this one. After fetching the data from the external memory, now the data is waiting here. After the execution is done, the previous execution is done, then that particular data will be given to this execution unit. Then execution unit will execute this particular data. So like that, all the 6 byte of information one by one, once the execution of previous data, once it is done, then it will take the next data for execution. Which one will take? Execution unit will take the data for execution. Till that, all the 6 byte information will be waiting in this instruction queue. Okay. So this process we can call it as pipelining.